In this video, we're going to talk about infinite limits. Suppose you have a function that looks like this. Function will be everything in blue, nothing else. And here's the number 7. Okay, that's in blue. There's 7. Here is a vertical asymptote at 7. And here is the graph as promised in blue. So what is the limit as x goes to 7 from the left of the function g of x? What is the limit as x goes to 7 from above of g of x? Now, each of these are infinity. As you can see, when x gets closer and closer to 7, but below 7, the graph is going up, and away. It's going to positive infinity. And when x is a little bit more than 7, it too is going up, and away. So those limits are infinity. They're infinite limits. Suppose you have this graph. And let's talk about 8 this time. And you have a vertical asymptote at 8. And the graph will be in blue. Maybe it goes like this, getting closer and closer to the vertical asymptote, and maybe it's going like this. So what is the limit as x approaches 8 from below of f of x? And what is the limit as x approaches 8 from above of f of x? Well, if you're a little bit less than 8, the graph is really clear, I hope. It's going to negative infinity. If you're just a little bit more than 8, the graph is going up, and away. It's going to positive infinity. Want to look at something. If you have a constant like 3 and you divide it by a very small number, so what's below this line is going to be a very small number, like 1 over this number. Well, the rule for dividing two numbers, if at least one of them is a fraction, and that's a fraction, is to keep the top number, change division to multiplication, and flip over the bottom number. Well, this number is quite big. And if you say, nah, it's not that big, fair enough. Fair enough. I'll make this number even smaller by putting more zeros. 1, 2, 3, 4, 5, 6 more zeros. Okay, that is, this number is now 10, 3 zeros, another 3 zeros, etc. Okay, well then this answer will be even bigger. I can make this fraction as big as I like by making the denominator smaller and smaller and smaller. And it doesn't matter what that constant is. If it was 13, then I'd have 130 whatever gazillion. Okay? If I had 131, then I'd have 131 gazillions. It doesn't matter. Actually, I'd have 131 and another 0. Oh, shucks. Okay, so I'd have another comma. The bottom line is, as this goes to 0, this whole fraction goes to infinity. This whole fraction goes to infinity. Now, if this numerator was negative and the denominator is positive, a negative over a positive would be negative. If the bottom were close to 0 but negative, and the top is negative, negative over negative will be positive. It would be going to positive infinity. If the top was positive and the bottom was negative, it would be going to negative infinity. A constant over 0 plus or minus is either plus or minus infinity. The constant is not 0. Like 7 over a very small positive number, or 7 over a very small negative number. And when I say a small negative number, I don't mean negative 39 billion. I mean close to 0. Close to 0. Now, let us talk about a vertical asymptote. Vertical asymptote. You have a vertical asymptote at x equal a if x equals a makes the denominator equal to 0, but not the numerator. That is, the numerator is some number different than 0. You have a vertical asymptote if an x value makes the denominator 0, but not the numerator 0. So, if I were to ask you to find the vertical asymptotes for the following functions, this should be easy. You have f of x equals 1 over x squared. You have a vertical asymptote at, well, what makes that 0 is 0, and when x is 0, the top is 1. The top's never 0. So, I found an x value that made the denominator 0 and not the top 0. Now, suppose you have f of x equals x squared over x squared plus 5x plus 6, and you want to find the vertical asymptotes, if there are any. Vertical asymptotes at x equal, well, the denominator, I just want to know when it equals 0. Well, I could fairly quickly come up with two numbers that multiply out to 6 but add up to 5, and those numbers are 3 and 2. So the denominator is 0 when x is 2, negative 3, and when x is negative 2. And neither of these numbers make the numerator 0, because when I square negative 3, I don't get 0. When I square negative 2, don't get 0. So we have vertical asymptotes at x equals negative 3 and x equals negative 2. Okay. Now, when the bottom is 0, the denominator is 0, if you can have a removable discontinuity or a non-removable discontinuity. So the question is, do we have a removable discontinuity or an non-removable discontinuity? Which one do we have? You can have both. Okay, so suppose f of x is x squared plus 5x plus 6 over x plus 3. Well, the numerator factors, we just saw, to x plus 3 times x plus 2 over x plus 3. Well, if x is not negative 3, we get x plus 2. That is, f of x, if x is not 3, is just x plus 2. It's just that line where it crosses at 2, except at 3, that point's not there. We don't have that point there. Now, we could, this is what's called a removable discontinuity, because I can define one point and say when x is 3, 3 plus 2 is 5. In other words, I can define f of x to equal x squared plus 5x plus 6 over x plus 3, where x is not negative 3, and I can define it to be 5 when x is negative 3. Now, remember, this here is x plus 2 if x is not negative 3. And I say it's 5 when x is negative 3. Well, you know what? That's just x plus 2 everywhere. Because even when you plug in 3 here, okay, I'm sorry, negative 3 plus 2 is negative 1. It's negative 1. Negative 1. But that's just x plus 2 everywhere. I just and this is continuous. I just redefined one point. I said, hey, when x is negative 3, we can be negative 1. Y can be negative 1. Otherwise, it had the open circle right there. I'm able to remove this discontinuity by just redefining, in this case, one point. But if it's a finite number of points, we're okay. If you just have to redefine a finite number of points. But then again, we're just talking about at one point at 3. This is a removable this function has a removable discontinuity at x equals negative 3. All I did was redefine that one point. What if you were told that f of x was equal to x squared minus 1 over x plus 1. Well, if you factor the top, it'll be x plus 1 times x minus 1 all over x plus 1. Now, as long as x is not negative 1, this cancels out to 1 times x minus 1 is x minus 1. This function and this function are the same, except that x equals negative 1. Well, I know how to graph f of x or g of x equal to x minus 1. It goes like this. But when x is negative 1, right there, the function that we have, f of x, there has to be a hole here. Well, if I just fill in that one hole, I'm okay. I'll just call it negative 2. Okay, I can redefine f of x. Let's call it f prime. This does not mean derivative. Okay, let's call it f star. F star of x, I could define it to be x squared minus 1 over x plus 1 when x's are not negative 1, and I can define it to be negative 2 if x is negative 1. Okay, and it filled in the spot. So now the graph is continuous. Hence, since I was able to redefine just one point, I just said, hey everyone, f of negative 1 equals negative 2. I redefined one point and I made that discontinuity continuous. Okay, this means that there is a removable discontinuity. This function has a removable discontinuity at x equals to negative 1. Suppose you have this function. Suppose capital F of x was equal to x squared minus 4 all over x cubed minus 4x. Well, if I factor an x out from the bottom, oh, I get x squared minus 4. I don't even have to factor the top. Okay? Well, maybe I do, just to see when I'm getting 0 over 0. You got x times x plus 2, x minus 2. Now this is equal to 1 over x if this is not 0 over 0. That means x is not negative 2. And if this is not 0 over 0, I'm crossing it out as if they're 1. The second condition was x is not 2. Okay. So if I were to graph this function, it would look, if I were to graph this function, it would look just like this. But now, to graph big F of x, I have to remove 2 and negative 2. I would have to remove that point and remove that point. But when it comes to the discontinuity at x equal to 2, I can remove this discontinuity. I just fill it in. So we have a removable discontinuity at 2. Same thing at negative 2. I just fill in that point. And now we can say we have a removable discontinuity at negative 2. This is f of x. Let me not use blue, because I'm about to say except where you see blue. This is f of x, but these 2 points are not there. They're not there. Okay, but I can make, so it's discontinuous at 2 and at -2. But again, I can fill it in. I can fill it in at 2. I can fill in at one point at -2, and I made it continuous. Now that's not always going to be true. Some discontinuities are not removable. Suppose you come to learn that h of x is x minus 3 over x squared minus 6x plus 9. Well, it turns out that the denominator is nothing more than x minus 3 times x minus 3. Now, as long as x is not 3, this cancels out, and I get 1 over x minus 3. Okay, now the thing is that that's a 1 over x graph moves 3 units to the right. It's as if the origin, so let me label these. It says, see, this equals 0 when x is 3, and I am adding nothing. So the vertex is 3, 0, which is right here. We make believe that this is the new y-axis, this is the new x-axis, the origin is right here. And I draw my 1 over x graph. And there it is. There it is. Now, at x equals 3, we do not have a removable discontinuity. First of all, this endpoint is way up there, and this endpoint is way down here. Even if we set it here and here, there's an awful lot of points that we'd have to fill in. There's an awful lot of points that we have to fill in. This is a non-removable discontinuity at 3. You just can't fill in one point and say, oh, now it's continuous. This is, if you could, we call that a non-removable discontinuity, a removable discontinuity. In this graph, we cannot fix it. We can't just redefine and say, oh, okay, h of 3 is 7, and now it's continuous. No. First of all, f of 3 is undefined. Actually, it's indeterminate because you get 0 over 0, and then when you look a little bit closer, when x is near 3, that's going to be near 1 over 0, which is plus or minus infinity. It's not going to be continuous by redefining a couple of points. How about this function? Well, okay. How about this limit? What is the limit as x approaches 3 plus of x minus 2 over x minus 3? Well, when you direct substitute, you're going to get a positive in the bottom. 3 minus 2 is positive. And it's not 0. I mean, okay, it's 1. It's 1. 3 minus 2 is 1, which is a positive number. In the bottom, we're getting 0. But if you have more than $3 in the bank, if you have more than $3 in the bank and you take out 3, you'll be close to 0, but you'll have something left over. If you have a little bit more than $3 in the bank, Yes, $3 and a penny. And you take away 3, you'll be close to 0, but positive. A constant over 0, or approaching 0, is infinity. Positive over positive is positive. What if you have the limit as x goes to 5 of negative 4x over x minus 5, and we're going to say plus? Well, the numerator, negative 4 times a little bit more than 5, is around negative 20. The bottom is 0 when I plug in 5, but this is a little bit more than 5. When I take away 5, it'll be positive. A negative over a positive is negative, and 20 over around 0 is infinity. In this case, negative infinity. What would it have been if it were 5 minus? A little bit less than 5. Well, again, the top will be negative 20, and when we plug in 5, and it'll be 0 when you plug in 5 in the bottom. But now you're a little bit less than 5. You have $4.99 in the bank, and somehow they allow you to take out 5. You owe them. You are negative. And negative over negative is positive, and a constant divided by near 0 is always infinity. And I should say a non-zero constant. This constant is non-zero. What if you were asked to do this problem? What is the limit as x goes to 0 plus of 1 plus 1 over x? Well, you have every right to use your limit rules and say it's the limit of 1 plus the limit of 1 over x as x goes to 0 plus. And we learned that the limit as x goes to anywhere of a constant is just that constant plus, well, now we have positive 1 on top and 0 on the bottom, but a little bit more than 0. So we have 1 plus infinity, and since the top and the bottom are positive, it's positive infinity. You don't need to write that positive, but that's infinity. If you have any finite number and you add infinity to it, it's going to be infinity. Another way to have tackled this problem could have been to get a common denominator. Think of the 1 as x over x. So now you have x plus 1 over x. And the top is going to get closer to 1, which is positive, and the bottom is getting closer and closer to 0, but it'll be positive. Now 1 over 0 you can't do, but 1 over close to 0 you can do. It's going to be plus or minus infinity. Since I'm more than 0 I'm positive, and since the numerator is positive, positive over positive is positive. And we got the same answer. I'll put the positive there. Do a couple of more problems. Suppose you were asked to find the limit as x is a little bit more than 1 of x squared plus x plus 1 over x cubed minus 1. Like always, you should plug in 1. The top is going to give you 1 squared plus 1 plus 1. The bottom is going to give you 1 cubed minus 1, which is 3 over 1 minus 1, which is 3 over 0, which is plus or minus infinity. We know the top is plus. What about the bottom? If you have a little bit more than 1, you have a little bit more than 1, and you cube it, it's going to be more than 1. And then when you take away 1, 1.001 cubed minus 1 will be bigger than 0. That's enough for me. If you keep multiplying a number that's bigger than 1, the answer will always be bigger than 1. If you do it a finite number of times. If you take a number less than 1, but not negative, between 0 and 1, take a number less than 1, and you keep multiplying it by itself, like 0.9. You keep multiplying it by itself. You keep multiplying it by itself. This is going to approach 0. Okay? If you take a number bigger than 1 and you keep multiplying it by itself for a long time, this is actually going to approach infinity. But more importantly for right now, that product will be bigger than 1. Okay? So what I'm saying is, if you're a little bit less than 1, if you're a little bit less than 1, if you're a little bit less than 1 and you keep multiplying it by itself, it's gonna go to 0. If you're a little bit more than 1 and you keep multiplying by itself, you're gonna end up with more than 1. If you're more than 1 and you cube it, that result will be more than 1. And if you have more than 1, maybe not a lot more than 1, but if you have more than 1 apple, for example, if you gave me an apple, you'd have something left over. Okay, and a positive over a positive is positive infinity. What if you have the limit as x goes to 0 of x squared minus 2x divided by x cubed? Well, if you directly substitute, you get 0 squared minus 2 times 0, which is 0 minus 0, which is 0. In the bottom, you get 0 cubed, which is 0. You get 0 over 0. That's not good. Well, then what I would do is I would try to factor out x minus 0 or x. From the numerator, I can factor out an x. In the denominator, I can factor out an x. And since x is not going to be 0, this cancels. So then I have the limit as x goes to 0 of x minus 2 over x squared. The numerator is going to be negative 2. The bottom is going to be 0. Now this is a problem. We need to break this one up. The limit as x goes to 0 from the left of x minus 2 over x squared, well, it's going to be negative 2 over 0 plus, which is negative infinity. And if you have the limit as x goes to 2 from above of x minus 2 over x squared, the fact that you're squaring the x doesn't matter whether it's a little bit below 0 or a little bit above 0. Because when you square a negative, you get a positive. And when you square a positive, you get a positive. The bottom is getting really close to 0. But as long as x is not 0, it'll be positive. And the numerator is negative 2. Negative over positive is negative infinity. Since we got the same answer, we could say that the limit as x goes to 0 of the original problem, which I think was this, is equal to the common answer, negative infinity. that completes the video on infinite limits.